Hello everybody, my name is Lena and I'm an engineering project manager here at Treble Technologies. In this webinar, you will hear from our customers who have used Treble's Acoustic Simulation Suite in their acoustic design projects. They will share their insights and experiences on how the software helped them achieve their goals and overcome their challenges. The agenda for today's webinar is as follows. First, we will hear from Bradley Alexander, an acoustic engineer from Bollinger Grohmann, a renowned engineering firm that specializes in complex structures and innovative designs. Bradley will show us how he used Treble's Acoustic Simulation Suite to observe local acoustic behavior in geometrically complex large-scale spaces. Next, we will hear from Ethan Bourdeau, the founder and principal of Bourdeau Acoustical Designs, sound concept lead at International Wellbeing Institute, executive director at Quiet Parks International, and part of the board of directors for Institute for Noise Control Engineering. Ethan will demonstrate how he used Treble's Acoustic Simulation Suite to plan and optimize the acoustics of various public listening spaces. And finally, we will hear from Finnur Pind, the CEO and co-founder of Treble Technologies. Finnur will introduce us to some of the new exciting features and enhancements that are coming to Treble Acoustic Simulation Suite. After the presentations, we will have a few minutes for questions and answers. You can submit your questions using the chat box at any time during the webinar. We will try to answer as many questions as possible within the time limit. We hope that you will enjoy this webinar and learn something new and useful from our speakers. Without further ado, let's begin with our first presentation by Bradley. Over to you.
Hi, everybody. I'm Brad Alexander. And first, I would just like to say thank you to the team at Treble for having me here today and producing this software. It's been a real pleasure working with you all since you brought the software out onto the market. I've been using the simulation suite since basically day one, and ever since it's been a part of my daily practice. I use it pretty much every day. Just a little bit about myself. I work in the building physics department as an architectural acoustic engineer for Bollinger Grohmann Consulting in their Berlin office. We're a large multidisciplinary engineering firm who specializes in structural engineering, facade engineering, building physics, sustainable design, and fire engineering. I received my Master's of Science from the TU Berlin, from the Department of Audio Communication and Technology. I wrote my master's thesis on numerical simulation methods for analyzing a broadband absorber device. And yeah, and I'm still to this day continuing some research projects or pursuing some research projects at the TU Berlin, also working with colleagues at the University of Arts in Berlin, where we are analyzing the absorption properties of generatively designed building components, smaller building components. Yeah, so at Bollinger Grohmann, we have the pleasure of taking on a large variety of project types in both scale and complexity. And often this requires fluid cross-disciplinary discussion between structural engineers and building physics engineers and designers. And we do everything from standard sound insulation reports for interior and exterior components, room acoustic consulting, acoustic measurements, and outdoor sound propagation analysis. So it's we have a quite diverse portfolio of what we do here. And in terms of acoustics, Treble has really become one of our primary tools for the room acoustic planning process. And what's interesting is that since we started using Treble, our project turnover rate has increased pretty significantly. You know, I mean, on the one hand, we're able to produce results faster, very accurate results faster, and we have, you know, good pictures of the results, and it's very easy to, you know, get the results into report format. And it seems that the architects that we've been consulting with on our ongoing projects are asking for more and more of these types of simulations. They're saying, okay, these, we get these results fast. They're good, they're reliable, they like the results. So they just keep asking for more and more simulations, and that's, I think, good for everybody. We can provide better consulting, and we have more to do. Yeah, and I think one of the reasons that they like this, as opposed to getting it quickly, is that as opposed to purely geometric simulation algorithms, which don't have the wave-based solver, is that, and this is my feeling, we aren't getting the extraordinarily long reverberation or modal decay times below 315 hertz, or some cutoff frequency, which a lot of times leads, or what usually leads to this typical, sloped curve towards low frequencies, which sometimes can complicate the planning process, because you get the feeling like, I got to put more low frequency absorption into the model, and as we all know, low frequency absorption takes up space. It's bulky. It's not always the most attractive or aesthetically pleasing part of the planning process. And what I'm seeing now is that based, from the results from the wave-based solver, you actually don't need it as much as you might think. We're getting shorter reverberation, or shorter decay times, statistically, like over larger areas, and it makes the planning process a lot easier. So you don't always have this slope, which is going above the higher tolerance, based on the room type, which always complicates things. So yeah, another thing is that the speed of the turnover is also allowing us to calculate, also in parallel, a larger number of model variations, where we can optimize or reduce the total necessary absorption area, and by finding the best surfaces to cover with absorption materials, to get the most effective results, or to get the reverberation time in check, in the right places. So as a result, Treble has basically put us in a better consulting position, because we can get reliable results quickly, and we can provide, and this is actually a good point, that we can provide more active insight into the consequences, into the design consequences, that interior planners are making, which makes for an easier and more fluid dialogue between the acoustician and the architect or planner. So we can also keep up with the pace of their design changes. So that, that's a big plus for us and for them, and projects can move along more quickly, and we can stay in the flow of the work process. So as I said, it's been a real pleasure using Treble. It's obviously I'm a fan, so I love it, and it's very easy to use. I like that it's SketchUp based, and when the Rhino plugin comes in, that'll have some benefits too. It's intuitive, and also I have to say the customer support has been incredible. Thank you all for helping me with my many questions and challenges that we've had, or I've had, since the beginning. It's been a real pleasure. So what I want to present today is basically how I have been using Treble to help me in large scale projects where the geometry of the architecture is complex, the interior design is complex, and where I wouldn't have been able to input the geometry into other programs in the past. Yeah, so we have multiple large scale projects going on at Bollinger Grohmann, where we are consulting on the design of so-called multi-use working atria. where we're seeing a variety of open spaces intended for different uses, like offices or eating areas or, different types, coupled to a large voluminous atrium. And as I just said, among these spaces are always working areas for office spaces. And obviously the acoustic conditions there need to be different than those around the circulation areas or the gathering spaces in the atrium. One of the challenges here is firstly setting realistic acoustic goals for the working spaces so that they fulfill at least one or more of the requirements or suggestions set by standards, such as the DIN 18041 in Germany. We also have the ASR A3.7 or the VDI 2569 for office spaces. And there are, certain situations where we just physically can't meet the requirements set by, for example, the ASR of 0.0 seconds. It's just not possible. So we need to think of creative ways to show architects, what they're planning is a good solution. We may not be able to meet this requirement or that requirement, but there's some other criteria that we can work with, and which we can show them that we're meeting, and we can improve the acoustics as much as possible to make the best possible working environments. And so since the building geometries are generally expansive and complex, it's pointless to estimate the acoustic behavior using tabular methods based on Sabine's formula. I mean, you can, but the results, I wouldn't say they're not reliable, but based on the amount of absorption area compared to the volume of these types of spaces, it just the math just doesn't work out because the volume is just so huge that you can't cut off one space from another. And I mean, don't get me wrong, I love Sabine's formula just as much as the next person, but there are just a lot of situations where it doesn't help. So this is especially apparent when we're working with coupled spaces, unequal distribution of absorber surfaces, complex geometries, and also it doesn't account for the position of absorber surfaces, and the local differences which occur in larger spaces where the volume is so large that it just, as I said, mathematically no longer makes sense whatsoever to try to even apply the equation. So before Treble came into the picture, a question which often came up was, how do we deal with direct and reflected sound energy, which leaves a room but returns as a diffuse field from the coupled spaces? One could think, yeah, no problem. Just look at the gap or the common surface area between the two spaces and assign that surface an absorption coefficient of, I don't know, 0.5 to 0 to 1, if it's but and that's supposed to account for the loss and decreased density and amplitude of returning energy, and just completely leave the coupled geometry out of the model. While that might be a good idea for shallow coupled spaces where the mean free path length is relatively short and the time delay of the returning sound waves is irrelevant, larger rooms with significantly different mean absorption coefficients will have a much larger time delay for the returning sound. And this delay can really only be properly simulated by modeling the space, the geometry, and the strength of the delayed sound's amplitude will be a result of the reflections and the absorption coefficients in the coupled larger space. Now, depending on the size of the primary and coupled room, the simulation time may be extended to a degree that modeling the couplet space no longer really seems practical, which is where Treble comes in. And the hybrid solver, which gives me both wave and ray type behavior, allows for a much better and analysis tool, which gives me a larger picture of how these so-called acoustic microclimates in, for example, working spaces are behaving with with specific source positions. And since the solver takes into account the wave effects below the cutoff frequency, I can also get diffraction around corners and around edges of furniture, and you get frequency dependent reverberation time at specific positions. And in addition to the macro or statistical observations of the space as a whole, I get the specific types of behavior at locations within the space. So what I'd like to do now is to switch to an example where I first, sort of started working with this problem, and later on, I'll in a second model, I'll show you how I used model variations to engage in dialogue with the architect to show them which surfaces and their materials are most efficient for improving the acoustics of the space as a whole, and also the smaller zones within larger spaces or middle-sized spaces. Okay, I'm going to start sharing. Okay. So what we see here is this is the first of the two models. As you can see, it's a large piece of architecture where there is a central atrium area with a large surface area, high ceilings, goes across all of the floors. And surrounding this atrium are the office spaces, which are to a more or less degree set off from the space. They're always on the exterior perimeters of the buildings, and the goal, the objective was to create a sort of an acoustic transition between this central area, which should, be lively. The reverberation time can be slightly longer. There will be events there, groups coming in and out, and so it'll be louder. To have a transition zone in between the office areas and the atrium, where there's a circulation route around the building, around the core of the building. And then along the edges, we have the office areas where the acoustics should be such that the reverberation time is shorter, it's quieter. And, we achieve that by planning room-in-room situations, screens, some absorption surfaces, sails, baffles, screens along desk areas. And the challenge here is to show in terms of simulation, is to show how these spaces behave when they're coupled along to this large atrium. And in the past, I would always try, as I mentioned, to model the space just as along the common surface area, along the edge out here. I'll show you in Treble what I would used to do, is just as an example. So I have the office here, and then along this edge here, I would say this has a set of absorption coefficients, which should more or less reflect what I think this space would do. And that just didn't really work out. It just, it's more or less impossible to decide on a set of coefficients which, indicate the amount of returning energy from that area into the space. And when you look at the results with a similar source position, for one frequency, you can see, oops, back to, yeah, it's much different. and you have to be careful of the legends because the colors switch between the source positions. So so for this area, I would, I put in a surface receiver area to get a look at how the reverberation time changes across the space as it, as a transition between the atrium zone and the office space, or the seating area within the office. And I can show that to the architect, saying, look, we're seeing the reverberation decrease the farther we get away from the space. And then, when I begin to export data from my reports, I can't rely on the A to V proportion, or in German it's Adeuchverhältnis, which is the proportion of the equivalent absorption area to the room volume, and the requirement is a function of the room height. Because you can't take the volume of this entire space. The volume of this entire space just dwarfs the total equivalent absorption area, and then mathematically it just doesn't work out. So what I do is I just take the inverse of the A to V proportion and multiply that by 0.163, say by its formula, and I get an orientation, or sort of a value which I would like to achieve, which doesn't necessarily work out because physically, it's very difficult to get, the required reverberation times in these areas because of the returning energy from this space. But, I use that as a goal to help me in the planning process and to adjust surfaces accordingly. And when I take the average reverberation times across multiple sources and many receiver positions, I set up, lots of receiver points so that I can take an average. I can show the architect how, on the one hand, the local, these micro climates are improving, and also the space as a whole. And I would do that for, more than one space. We usually do a set of spaces and show, look, here's the transition zone from shorter to, or from longer to shorter. And do that for different parts of the building, as opposed to just looking at this entire section as a whole. So I look at the smaller area for the planning process, and then I take my averages for the reporting. And, that's how we, move forward in the planning process and in the dialogue with the architect. So I'm going to switch over to another model now. Here, which is a, a building, slightly different. We have an atrium on the side of the building, which is basically just interweaves the entire space. The office areas on these terraces aren't even cut off physically from this area. So the situation is much more challenging, and the it takes so a little bit more planning and a little bit more looking and analysis, and to figure out how do we decouple this space, or decouple the acoustics from the space to an extent to make this area comfortable enough to be able to work in, at least acoustically. And so what I did here was I set up, many different variations on the space along, just hide this, on the model, where I vary these individual surfaces, their coefficients. I have, this banister here, which is this is glass, so I would take some perforated plexiglass here, or put some absorption area on the inside of the banister in terms of micro perforated plexiglass. Some models have acoustic screens here on the desks with different heights, different widths, different absorption coefficients, carpet. The ceiling has absorption. The back wall has a curtain. This room-in-room situation will have some absorption along that wall, and I vary the properties of all those things to find out, which surfaces have the best effect on the individual zones, which I want to show. And so when I go up here, when I began the dialogue with the planner, I was showing, look, we have sound sources from the atrium area, from this middle zone out here, and also from the wing, from this office area, where we're going to see, not only sound coming in from that incident sound, but we're going to have reflected sound coming out from this area, this office area. So I set up my sources to sort of model as a transition area between these source area and the reflection areas. And I use that to break this space up into smaller zones, which I was calling acoustic microclimates, and see how I can improve these individual zones, these smaller zones, by adapting the surface properties of the near surfaces accordingly to, improve the acoustics of that individual space and improve the acoustics of the space as a whole. So, in the past, I would, and when I go over to Treble now, I would so here's the model, which you can see. I didn't have receiver areas, surface receiver areas in the past. I would do these with point receivers, but now that these surface receivers are there, it makes also visualizing the acoustic microclimates much more interesting and fun. You can really get a sense, at least for individual frequencies, tend to use 500,000 hertz to show the behavior, how sound energy returning from certain parts of the room behaves in these different zones within the space. So I can, switch between sources. And, like I said, when looking at this as a whole, I do take statistical results. I average all of the data to get a big picture, but in the planning process, I focus on the behavior of the individual zones. So what I would do is I would model and simulate all of these different variations, and Treble makes it very easy to export the results of specific parameters. You just click on report view and pick the parameter you want, set up all the sources that you want to look at, and you can choose either individual receivers or all the receivers. I would choose the individual receivers for the zones and take an average over those, and then export those results, or copy those results into Microsoft Excel. And here's all the data of the space, compile all that, for myself, and then show the curves to the architect to communicate to them how individual design decisions are affecting the acoustics of the space, and figure out which decisions are most effective for the whole area and for individual zones. So I go back to this PDF real fast. So if I, you get, like, for example, for this variant, you can really clearly see how, each one is a different zone, how each zone in the model has a significantly different reverberation time for this specific variation. That showed to be extraordinarily helpful, because we realized, oh, okay, this the let's say the perforated panel along the banister, the perforated plexiglass, I wasn't providing the results that I would have hoped. Wasn't effective, especially not for these back areas. It can be expensive, and they bring this data, especially these single number values, to the developer and say, look, we have maybe 3 to 4 variations. We can expect these results, and that they move forward with their decision making, and then come back to me and say, okay, now we'd like a variation on this model. And so that's how we go. We go through iterations of each one. And so, I take the data back, I input that into the model. I can simply, change I go back and I just, I duplicate the model. I can change surface properties by adjusting the absorption coefficients, add new materials. In SketchUp, I can just upload a new model real quickly, and then apply the same simulation and with the adjusted surface properties, and then compile the results again. And it makes it very easy, and makes for a very fluid communication process between myself and the architect, and then also the developer, for getting these large, acoustically complicated designs to the point where we have, acceptable to very good acoustics for certain zones of the building. And I would look at the wings here and the middle zones, and also the atrium. And the greatest thing is you also learn a lot about how sound behaves in a space by working with these models, and by setting up these surface receivers. And I also look at the sound pressure level in the area, but mostly I do look at reverberation time. And then in the end, I have in the planning process these zones, which I discussed, and I have the sources for each zone where I think the highest energy density will be, which will have a large effect on the reverberation time in that specific area. And then I have the entire statistical results of the space, which are used for reporting and for communicating with the other developers, and with the developers and the architects. And all in all, the planning process has become faster, more efficient, more clear, especially with these visualizations. I don't have to explain how sound pressure level decreases over a space from a specific area, because I can just show them right on this surface map. And I also don't have to explain why I think the reverberation area will be different in this part of the room as opposed to this part of the room. I can just show them. And people, they really they believe it. They do believe it when you tell them, but when they see it and they see that it's been calculated and simulated, it makes for a good conversation, and less confusing for everybody, because you get a visualization of the results. So yeah, that's how I use Treble to work with these architecturally complex and acoustically very complex spaces, and these coupled spaces, where in the past there would have been a daunting task trying to figure out how do I separate these rooms acoustically from this larger space? How do I model that? How do I set up the simulation to get reliable results? And now it's taken so many variables out of the equation, so that I no longer have to rely on estimates. I can just build the space. I have all the data of all the surface data from the architects. I set up the simulation with the appropriate absorption coefficients and the scattering coefficients, and then I just run the simulation, and it's fast. The hybrid model. Sometimes I just do a survey, the geometric, just to get a quick result. But the hybrid model, the solver is just it's extraordinarily fast, and I don't have this low frequency problem. as much as I used to. And it's been, as I said, it's been a real pleasure working with this software. Again, thank you to the team. Thank you so much for the support. And just I'd like to say just to keep up the good work and implementing the suggestions and implementing new features. And I'm really excited to see how Treble develops in the future. So thanks.
Thank you, Bradley. Please post your questions in the chat box for later. And now over to Ethan.
Hi, everyone. I'm Ethan Bourdeau. Just want to say thanks to Treble and Finnur for having me on this webinar to discuss my experience with the Treble software so far, my involvement as a beta tester, and how I've been using it on a few projects that I'll share with you that are quite interesting in sort of the public listening room style of space. Primarily with limited budgets. So a lot of interesting quirks that emerge when you acoustically model spaces where there are limitations like that. But yeah, my background is as an acoustical engineer, also serving as the sound concept lead at the International Well Building Institute. I was fortunate to meet Finnur during my time in that role, and I've really been excited to see how his work with Treble and developing this product has turned into something that I now use regularly with my clients on the side. In addition to being an acoustical consultant too, I'm also now the proud owner of the world's tallest cat tower behind me, which we just erected this weekend. So I promise it won't be the main event for the rest of this discussion, but yeah, I want to just dive in and talk about two projects that I was just super excited to leverage Treble's capabilities with this past summer. So let me just load my screen. So the first of those two projects that I'm going to share about is this listening room concept that my partner Devin Turnbull, who some of you may know of Ogis Loud speaker designs and turntable hi-fi equipment, was commissioned to create the second installment of an exhibit that was originally premiered in New York City at the Listen Gallery. This time it was being premiered in London at the Listen Gallery's location in 24 Bell Street, just north of downtown. And this was a really interesting project because there were so many limitations. We were aiming to recycle acoustic panels, simple 1 and 2 inch panels from previous projects that the gallery had used in the past. Devin was also designing a brand new system for this that I had not previously listened to before. So finding the right balance in the room with surface finish materials and layout was going to be a challenge for a number of reasons. For those of you who are keen enough to observe the super sub against the wall, I can assure you I did everything in my power to make sure that's not where it ended up. But it was really interesting to look at this room virtually and also speak with the client over the process of design to ensure that we were using and recycling the materials from previous exhibits effectively, and also creating some new materials as well, such as this back rear pedestal podium to act as a low frequency absorber as well, which we were able to model quickly in the simulator. So this is an actual photo of the exhibit. It only ran for a short amount of time, so this is no longer up and running, but I will tell you about one that is currently up and running here in New York for those of you who are able to venture out. So this was a view of the rear wall. We had 4 main planes of interest. We had left and right walls that were treated with fabric wrap panels, and also ceiling panels that were suspended to maximize the airspace behind it, with also some additional fiberglass treatment in addition to the panels themselves to create more of a low frequency absorption in that center of the room. Additionally, as I mentioned, we have this concept that we've sort of been pioneering with this resonating podium seating area. where you may notice it in the actual photo itself, but maybe it's clearer in this version. There are these holes that are cut out in the front face of this fabric wrapped kind of fascia of the podium, where sound goes into this and then is absorbed inside. So we're working on ways to tune this relative to rooms and relative to the systems that Devin's designing. With so many moving parts and limited ceiling height in here, we were limited to really its full effects. This is a front view of the systems, a photo I took while I was in town commissioning the room. You get kind of the sense of this outlying untreated wall that's more or less served as a kind of visual stasis. So when you're looking at the speakers, you're really focused on them and you're not necessarily drawn to the fabric panels. So that's not always ideal when designing these listening rooms, but it was really interesting to see how this lack of treatment on the front wall showed up in the model itself. And I'd be remiss not to mention that we do have a nice good bed of carpet throughout the room itself. So I'll take us now over to Treble, and we'll take a look at just how exactly this shook out. So an interesting part about this room is that it was separated by another volume only with a curtain. So when modeling this space, I found it especially useful to model the coupled volume effect that you might experience as a listener, especially one located, in this case, on the sort of left corner of the podium closest to that space. So to what effect did any slapback echo or that coupled volume have on the listening environment? So really it was interesting to hear that in this model. But I have modeled in here a few elements. We have sources that represent the loudspeakers, 1 and 5 for left and right. There's a center room omnidirectional loudspeaker for understanding the room response itself. And then these talkers 2 and 3, just to get a sense of what chatter in the other room might sound like. So this was something that the client was curious about when we were selecting the degree of acoustic treatment possible with this open door situation, which ultimately ended up being a fabric curtain that remained open the entire time. So it was really useful for us to model this in advance. And then a few receiver points in that room, and then also on the podium and in the DJ position in the front. So a couple things we can actually, I think if I shared this correctly, we can listen for a hot second. Let me do that one more time. Okay, so we should be able to listen now. So if we view from the podium seating, we have our USM modular furniture, a table in the middle. We're seated on the podium. You have direct line of sight of some of the talkers in the other room, which I currently have muted. But I usually listen to a few select tracks, which I upload in left and right. So I have a left speaker track and a right speaker track of a separated stereo audio file, which in this case is Blue Nile. Bounce around. I just love how like you get some of the drama of the low frequency on this. Maybe a little too much, a little clipping there. I know it's but then if we go in the other room, we get to hear this entirely untreated room's interaction with the somewhat treated or heavily treated listening room. And then the reverb tail. This is pretty close to how that room sounded. So when we did end up going out to commission the space, there was definitely that low frequency warmth, which just by virtue of there being no low frequency treatment in this room due to limited budget. But there was definitely, and we can actually observe that too if we were to maybe exit the oralizer and go and look at the surface receivers that I have set up in this. So if we look specifically in that low frequency range for, let's do center time. There's definitely these moments where that sound lingers, even in the listening, primary listening place on the podium, but it does keep itself in the corners, which is something we planned for with the location of the podium itself. So it was very helpful to identify those and then have that be a way that we define the extents of where people will be seated, which is something that even outside of a listening room capacity is really useful when discussing with clients, just visualizing the actual physical location of where sound will build up and where it may be uncomfortable or uneven or what have you. So at 63 hertz, if we look at strength, yeah, a lot of corner activity. Not the worst distribution of energy on the podium itself. And let's see, we're looking at just the left speaker. So we can look at the center omni channel, which I may have set up as a subwoofer, I think. But that becomes a bit more excited when looking at just the sub itself in the center of the room. But now looking at higher frequencies too, let's maybe not look at the sub for that. And then comparing how with this wall having the opening versus the right speaker, just how that ratio of direct and late reflections create and paint this listening position. So super useful. I'm super excited to see how the loudspeaker uploads and capabilities begin to evolve. I'm also super excited to get some of my more fringy bespoke loudspeaker designer friends to create CLF files. Some of them have GLL files, so I'm excited to see them find ways to convert that, which I think you can do in some programs. But this was especially helpful. We were really excited with just how things came out. There was, and I'll go back to the slideshow actually for this. Yeah, we were super thrilled with the turnout of this space. One thing that I will be publishing at some point will be comparing the treble data to Iris 3D by Marshall Day, impulse response data that I gathered while I was there, just seeing how they compare and what are some ways that we can continue to improve the modeling techniques to prepare for this type of space, which we'll have a few other iterations, I imagine. This is our second time doing this with the Listen Gallery. We hope to do a few others. They have a few other locations. And when we rolled this space out over the short period of time, the museum actually in the gallery saw its highest number of patrons on the last day, averaging around 700. This queue that you see here at the bottom left photo lasted I think it was a 2.5 to 3 hour wait, and some people were only able to hear just 4 minutes of one song by the time they got into the room. So this was a much hyped event, to say the least, and there were many collaborative record label events and other types of DJs that were present. So it was really unique to see people interact with a space that underwent this type of virtual acoustic modeling. So the second space that I want to share with you too is actually a more more permanent example of a listening room that is located here in New York City. It's based in Soho, neighborhood of Soho, in the USM Modular Furniture showroom retail space, which what you're looking at now is a photo of this back office environment that they've had in this space for some time. They had heard about Devin Turnbull's equipment for a number of years and thought this could be a good way to pair what their furniture is currently being used for, which is there's a niche market for hi-fi listening, individuals buying their shelves and furniture and using it for like turntable stands, monitors, stands, and loudspeaker sort of support. So we were brought in on this project about a year and a half ago to conceive of the best sounding listening space that we could have, and hopefully partner with some great manufacturers to outfit the room. But it's certainly not without its challenges, as you can clearly see on this front wall, which is actually now the right wall. We have just this massive glass, which is a double height space almost, and this movable door, which is on the far right here. It's super, super heavy. This is a very massive glass wall. And then there's this wood cabinet in the front, which was quite difficult to conceive of acoustically in terms of what we could possibly do with this. It will remain in the room. We can find ways to visually hide it, but how do we treat this in terms of the acoustics? And then on the left, we have this glass skylight that we tried to keep intact as much as we could, but you'll see in a second how we went about dealing with this. There's drywall directly on the building envelope, and then these three windows. One of them is operable. There's actually an outdoor porch that is in the rear of this building. So the goal was to build steps that would go out there. We would recreate that podium style seating in the back with 2 tiers. And then speakers would be on this wall in the front, located in front of this wooden cabinet area and in front of this other glass that separates this office from the next door office. So here's a look from the podium of how it's going now. It's going great. It sounds a hell of a lot better than it did when I first dropped by to take my impulse response measurements. We have a smaller super sub in the middle of the room here than that listen gallery space. Still the same 31.5-inch Fostex driver. And then we have 2 smaller, not the traditional Western Electric multi-celled horns, but still multi-celled speakers here and on the left and the right. And what we were able to do, you may notice on the far right here that there is no more glass. This is something that Quadra Acoustics was able to help us with in terms of finding an acoustic treatment that could magnetically attach itself to that glass wall structure, but also be consistent throughout the remainder of the room, where we have this treatment on the ceiling in a cantilevered suspended ceiling format that only slightly covers that glass skylight. And then we have it along the walls and along the rear wall as well. So take you back to Treble. We'll listen to that a little bit and then I'll wrap up. So here is the existing room. This will be interesting comparison because I have the original construction here as well. So we can hear what the system would sound like if we had done nothing versus what we ended up doing. So in this configuration, we have the quadrat ceiling called out. I'll just exit the oralizer really quick to show you how we ended up adding that in. So this is the quadrat ceiling suspended. We used, I'll have to send the link to exactly which product we ended up using. And then also used one of their wall panels as well, where we were able to easily access that data. What we weren't able to access was how the panel performs when it's offset from the glass wall, from the magnetic system. So it would be really interesting to take some measurements after the fact, which I've yet to do, to see exactly what the performance, how that differs based on how we were able to physically mount it to the glass, for instance, versus the direct mount on the rear wall and the side walls. So go back to the oralizer here and open the room. Of course, I lost all my sound files. And for this room, this is fun to listen to something that's a bit more clicky and transient. I sharing audio? Let's see. Yep. This is Murkoff for those of you keeping score of the music at home. A little bit of clipping. I'm not sure if that comes through. And then compare this to the original. We were able to significantly reduce a lot of reverberation time in this room, such that there's definitely, and I just listened to this piece in this room yesterday, there is a significant amount of low, mid to extremely high range clarity in the room. What I do find, though, is in designing these spaces, there tends to be this sort of psychoacoustic preference for just a lower frequency energy relative to the room acoustics, and that's certainly present in this room. If we can just quickly look at the results in the treated scenario. This takes a second. Interesting. Not sure if I necessarily buy this. We do the center omni. So this makes a bit more sense. And with the amount of absorption that's on the left and right walls, it's certainly not surprising, at least to me, that this mid to high frequency is relatively flat. It's a very consistent treatment throughout the entire space, even at the ceiling. But what may be lacking is the fact that this is directly mounted to the building envelope wall, the rear wall. So there's very little low frequency that's happening in the control that's happening at those planes. So there is this bump and this warmth. My guess is that the actual measured value in this room, once I get to it, will probably be about 0.05 higher than this, maybe throughout the first 4 bands. When we were comparing this to Excel models for a while, this was more of a linear taper from 63 to 1000 hertz, which is generally how these rooms are designed from my perspective. But this is pretty close to what I would say this room is responding to currently. Just go through each of the clarity matrices and center time. We can go to different listener positions. We do multi-select, get a chance to see the various positions averaged versus a single position. So yeah, what's beautiful about this room too is that it's going to be ours for quite a while in terms of how we can tweak it and where we're going to take some of the room acoustic treatments. There's a number of low frequency interventions that we still haven't deployed yet in the space. So we'll be excited to look into that. And our partnership with Quadrat was really fruitful in that we hope to provide and give some maybe white paper discussions at some point that focus on how the treatment is currently working and how it may suit a similar space in the future. But that's really all I had for this presentation. So happy to really dive in deeper on any follow-up that you may have. If you have any questions, I'm more than happy to be a resource. I am also super excited to share any examples that aren't listening rooms. I've been fortunate to work with architects that are really excited to use this software themselves, and they're really interested in finding new ways to visualize acoustics for their clients that care about certain themes like acoustics for neurodiversity, inclusivity, health and well-being, corporate office space, education, healthcare. So while this is a really niche example, I'm more than happy to be a resource with how you might use this in ways to communicate with architects and also their clients for a range of project types. So that's all I've got. Thank you so much again to Treble and Finnur and team for having me, and I look forward to hearing from everyone. Thanks.
Thank you, Ethan. Again, please post your questions in the chat box for later. And now for our final presentation of this webinar, Finnur, over to you.
Okay, hello everyone. This is Finnur Pind from Treble Technologies. I'm really excited about today's webinar. I'm excited to be showcasing some new and very cool features in the Treble Acoustic Simulation Suite. Before I dive into that, I just want to thank dearly the two speakers who spoke before me, Brad and Ethan, for their really interesting case studies and presentations. Okay, there's actually quite a lot I want to simulate here, and time is limited, so I will try to go as fast as I can so I can cover everything. First, I want to give just a very brief overview of the Treble Acoustic Simulation Suite. I'm sort of assuming that most people here on the call are familiar to some extent with our software, but just in case there is someone brand new, then I'll spend 30 seconds giving a very high-level summary of the product. I'll then just spend 2 words talking about a very exciting upcoming event in October, which is the launch of Treble's second product, the Treble SDK, and then move on to the main part of the presentation, which is showcasing a bunch of new features and improvements. First of all, the ability to import loudspeaker data in the CLF format into Treble and be able to simulate the interaction between loudspeakers and rooms, and also showing our new loudspeaker database, which is growing these days and will be growing over the coming months. Some very cool features relating to oralizations, being able to set up a particular oralization and save the settings that you set up, and then revisit them later, compare different setups that you have set up, and be able to share your oralizations with collaborators, clients, and so on. Not less cool is improved geometry processing, being able to import less perfect models into Treble, room models, and work with them further. The ability to compute open office parameters, such as distraction distance and things like that. A feature which we internally here at Treble call auto stop. Maybe a more precise name would be something like energy threshold termination of simulations. I'll show what it is, and it's a really cool new feature which improves efficiency of simulations. A neat little feature, being able to copy parameter results from Treble directly into Excel with just one click, and some small UI improvements here and there. And then we will move on to the Q&A part of the webinar. So without further ado, Treble, the platform, is a platform of virtual sound, meaning it's a piece of software that can do sound simulation on the one hand and sound rendering or oralizations on the other hand. And the sort of centerpiece of our platform is our proprietary simulation engine, something that we're very proud of and have worked on, or is the fruit of many years of R&D, where we are combining wave-based simulation methods for low to mid frequencies and geometrical pressure-based geometrical acoustics for high frequencies. And this engine allows people to do more accurate and more efficient acoustic simulations than what has been previously possible. The platform is then structured in this way. The simulation engine is based in the cloud, which offers a lot of flexibility and scalability. And then we are essentially building 2 interfaces to this simulation engine. On the one hand, the simulation suite, which is the product I'll be talking about mostly today, a graphic user interface tool to design acoustics. And on the other hand, the SDK, which is more a programmatic interface to the simulation engine. Now, the simulation suite itself. There are a number of use cases that this tool is suited for. From the get-go, we have perhaps mostly been focusing on room acoustics and architectural acoustics design. This is certainly one of the main use cases. But now, from today, we are launching some very powerful capabilities to be able to model sound systems in the product. It sort of marks our first step into the world of electroacoustic simulations, which we will then continuously be improving over the coming months. Treble or the simulation suite is also suited for outdoor sound simulation, maybe not at the level of sort of doing noise mapping of an entire city, but more sort of local projects such as analyzing the acoustics and noise in a building site, shaping buildings to improve acoustic conditions in the local environment, urban acoustics, designing traffic noise barriers with great precision, things like that. And then we have some really powerful oralization capabilities as well, which allows people to set up and design soundscapes, not just acoustics. And what we're trying to bring to the table with this product is essentially 3 things. First of all, better accuracy of simulations, which in turn reduces risk, improves confidence, avoids over design, things like that. And this is brought about through our sort of state-of-the-art simulation engine. And then secondly, a very strong emphasis on making the whole workflow around working with acoustics and doing simulations more efficient and seamless. The whole thing is based in the cloud. You can run simulations from any device, run as many simulations as you want simultaneously. You can collaborate with colleagues, have tried to have a very nice user experience, user interface, and so on. And then last but not least, because we can do very accurate acoustic simulations, then we can also do perceptually authentic oralizations. And we're also just trying to make oralizations more interactive, immersive, and just more fun. The way it's structured now is that the simulation suite is live linked to SketchUp. So we have a plugin in SketchUp that connects the two tools. But soon we will be launching plugins and connections to other 3D modeling tools such as Rhino and Revit. So please stay tuned for that. Okay, that was the simulation suite. Just wanted to say one thing here about the SDK. We are launching it officially on October 17th. So please mark the date in your calendar if you're interested in this. This SDK is useful for many exciting things. For example, setting up thousands of scenarios to generate a lot of audio data or acoustic data, which you can then use to train all kinds of machine learning algorithms like speech recognition or de-reverberation. Being able to do more advanced acoustic analyses, integrate our simulation engine into third-party software tools, and do parametric studies, for example, setting up from a scripted input thousands of permutations or of receiver positions or materials or things like that. Okay, that was the SDK. Now moving on to the main part of the presentation, showcasing these new features and improvements. And I'm going to move over to the Treble Simulation Suite now. Okay, here I am in the simulation suite, and I'm going to play around with this open plan office model today. A couple of minor UI improvements already seeing here. For example, these little nice buttons here that allow you to directly access or the oralizer or results, and also kind of a more direct access to resources such as tutorials and so on. And I also remind of our live chat, which if you're running into any problems or any questions, please write us there and you'll get an answer very quickly. Okay, I'm going to open this open plan office model here. And the first thing that I'm going to show you is our new loudspeaker modeling capabilities. So I've set up a simulation here. I'm going to move this guy over here. I've set up a simulation for this room where I've assigned some materials and scattering coefficients and so on. Then I put in a couple of omnidirectional sound sources and some point receivers in the space. And what I want to do now is change these speaker sources from being just omnidirectional to being some particular loudspeakers. So I'm going to click this button here, and then I open up our loudspeaker library. And it's decently sized already, but we will certainly be growing this over the coming months. We are in dialogue with many of the biggest loudspeaker manufacturers these days to get their data into Treble. And I'm going to, for example, place a ceiling speaker here in this position here. So I'm going to categorize and just show ceiling speakers. For example, just choose this QSC speaker. I can look at the directivity patterns and things like that here. And I'm just going to go ahead and assign this speaker here. And for the other source position, maybe just have that be some kind of Marsden audio speaker. Why not? Maybe this one here. Okay. Now I've kind of introduced two loudspeakers into this room, and I can do room acoustic analysis with these speakers in the room. I can do oralizations and sort of assess the interaction between the speaker and the room. I could also import my own loudspeaker into the tool if it isn't in the database. Let me show you quickly how this looks. Then I go here and import a directivity pattern, drop it here, and it gets into the library. Simple as that. Okay, now I'm going to run the simulation and also show you another really cool new feature, which is this auto stop feature. So typically when people do room acoustic simulations, they need, up until now, have needed to kind of set the impulse response length of the simulation, how long of a simulation impulse you should simulate. This means that you kind of have to guess beforehand roughly how long you think the IR is going to be. If you put it too short, and sometimes you don't get, for example, the T30 reverberation time values because you don't have enough energy decay in your impulse response to calculate T30. If you set it too long, then you may be simulating something that you don't really need. The energy decay from -50 to -60 doesn't really give us any information. So it's kind of waste of compute resources and time. But now with Treble, you can just say how much of an energy decay you want to simulate, and then we simulate up until that point and terminate the simulation there. So for example, saying I want a 35 dB energy decay, that means that that's enough to compute T30. If I'm in a bit more of a hurry, I can say, just 25 dB, and then I can compute T20, but not T30, and so on. So that's a very nice new feature. And I'm just going to fire off this simulation here. It does tell me roughly how long the IR will probably be, but the energy decay will dictate that exactly. Now a machine is spinning up in the cloud to run this simulation. And I'm going to come back to this simulation and these results in just a second, do some organization stuff with it. So I'm going to create one more simulation, duplicating this simulation that I just set up. So Acoustic 2. And I'm just going to change the ceiling material here to a concrete ceiling, just to have a bit of difference when we do organizations later. Otherwise, I keep everything the same and just fire this one off. All right. While we wait for this, I want to show you a couple of other really cool new features. So I'm going to go to a different simulation here and show you these open office parameters. So the open office parameters are measures of acoustic comfort in open plan offices. And open plan offices are one of the trickiest space types to do acoustic design in. And the way the standard specifies working with this, the ISO 3382-3 standard, is that you set up a sound source and then you set up sort of a line of receivers, and then you compute these parameters from kind of assessing the results across these different receivers. Now, I have already run this simulation, so I'm just going to go directly here to the results. Move this guy over here now. And we see a new parameter here, OOP, Open Office Parameters. If I click it, actually shows nothing. That's as expected because I'm just showing the results for one receiver now. But if I add additional receivers, I'll just add all the receivers, then it can compute the open office parameters across these receivers. I'm going to add a comparison here. And that be for all the receivers as well. This one here was open office 2, had an acoustic ceiling, whereas this one then had, a concrete ceiling. And what we see here in the results, obviously by adding the acoustic ceiling, we increase the distraction distance, we improve how fast speech is decaying over distance, the sound pressure level of speech is lower, etc., as one would expect. We can analyze this for different background noise levels and so on. So a very efficient, simple way to analyze open plan office parameters in Treble. Okay, the next feature I want to show you is just a neat little feature, but still I'm a big fan. It's this notion of being able to copy results from Treble and, for example, into Excel if you want to work with them there. Now, we have tried to build a very nice user interface to analyze results and so on. You can also save the pictures and compare results and everything. But sometimes you still just want to convert these or copy them into different tools. And we've had from day one the ability to download results where you get the impulse responses in an Excel sheet with all the parameters and so on. But now it's just a little quicker way. If you just want these parameter values, you just click this little button here. They're copied to the clipboard. I go to Excel and I've set up this little template here with some kind of graph. And I just paste Control V here, my results in here. And now I have them in Excel. I have 2 lines because I had 2 simulation comparisons there. If I had more, then I would have more lines, or if I just did the one, then I would just have 1 line. So a very easy way to go from Treble to Excel. Okay, now I'm going to go back to the simulations I was just running before and show you some really cool new auralization features. So let's take a look. Here we go. These simulations are done. I'm just quickly going to refresh here and go to the auralizer. So, as I'm sure most of you are familiar, in the auralizer, we can listen to the space. We can jump between different receiver positions. We can compare different simulations on the fly, for example, different material configurations of different models and so on. We can select different sounds on the fly. This has been available all along. But now we're introducing this little button here that allows us to save some kind of setup of an auralization that we have done and compare them between each other and also share them externally. So let me just create a little auralization here, maybe put some drum loop and these boys talking here. If I play here, this is the dry sound. Then I go into the space. Now I'm hearing the space with these particular loudspeakers in them. And then I can go here and I can save this little setup, maybe just for fun. Let me just modify things a little bit, something like that. And then I can save it here. I'll call it Drums and Boys. And then I can modify something. Let's maybe, oops, I'm not going to do that. Let's maybe change this to jazz here. And then I'll save that one as maybe modify the volume a little bit, because why not? And I'll save this one and I'll call it Jazz and Boys. And now I can compare them on the fly. Which is really nice and really useful if you want to come to the auralization later, for example. And last but not least, the ability to be able to share the auralization. I've now set up this particular auralization. I've carefully crafted my auralization, and I can either input an email here, like my own email, then click the button, and then I will be sent the link, or I can just copy the link to the clipboard and send it to someone. And what the person on the receiving end will then receive is basically a sort of read-only auralization here. They cannot modify the settings or so on, but they will basically get a view that looks something like this, where they can basically hear the auralization, flip between different design options, flip between different receivers, and so on. Almost all of the features I'm showing today are launched or are about to be launched within the coming days, except for the shareable auralization that's coming in a few weeks from now. Okay, that was the new auralization features. The last feature I want to show you is our new geometry processing algorithm. Now I'm going to go back over to SketchUp. This is SketchUp. Now, what Treble has required up until now is if you wanted to do a wave-based acoustic simulation, which is of course a more fun type of acoustic simulation, at least from my very biased opinion, then you would need sort of a quite perfect model to work with. It had to be, for example, watertight. So now I'm going to show you how we have sort of managed to relax the requirements on the geometries and still be able to do acoustic simulations on them. I'm going to go ahead here and import a particular 3D model, which I happen to know is not perfect. This is a model from a round-robin study. And I'm going to try to import it into Treble in sort of the old way. So I'm going to open the Treble plugin here and create the Treble folder. I'm going to pull the layers in the 3D model into geometry layer, and then I'm going to try to check that the model is okay. Using the old approach, which is sort of a locally implement, something that's implemented into SketchUp that runs locally on my machine. I check it here and it complains the geometry is not watertight. So I will then, what I could do before is I could click this button here where it would sort of highlight where in the model we have issues. For example, here there's a little sort of slit here that's an opening. It's not glued together. I could go ahead and fix that, and that can be a bit of a tedious process. I've always had the option of just uploading it as a non-watertight model and then be able to just run geometrical acoustic simulations on it. But if I wanted to do a wave-based simulation, then I would have to fix this. But now, with our new geometry checking algorithm, this can be automatically fixed. So I'm going to rerun the check. I just need to make some modification of the model so I can rerun it. I'll just rename this layer here. And then I'm going to try this cloud checking. It's still a beta feature, but will be launched very soon. So I'll check the model in the cloud. It takes a bit longer because it needs to send it to the cloud, do the checking, and then do the automatic healing of the geometry, and then return some information back. We're also working on making this faster, of course, but let's see. I'm expecting it to be done in any second now. Here we go. Now you see. No complaints about water tightness. The geometry has been fixed automatically. And then I'll just upload it here, create a new space, call it round robin, like so, and function 1 or whatever. Upload it, open it up in Treble, and now I can run a wave-based simulation on this model. You will see that the geometry has been fixed here. So just a step in the right direction towards making the whole geometry process even more smoother than it's been before. But we're continuously working on making this even better, integrating with BIM tools and things like that, which are on the roadmap. So that kind of concludes my presentation, or this presentation of these many new features. I do want to make a note that it's less than 3 months since we had our last feature announcement webinar, where we were announcing a bunch of new features. Surface receivers, new scattering modeling, 50% speed up of our wave-based solver, also speed ups of our geometrical acoustic solver, own sounds in Orlizer, many new things. Now we have all of this, and you can certainly count on that in, let's say, next 2 to 3 months, we will have another webinar with a bunch of new features as well. So there are many exciting things going on at Treble these days, and the sort of pace at which we are continuously improving the product has really increased. So that's very exciting. Last thing I want to show is that we're also putting out a bunch of new validation studies all the time. So here on our website, if I go to resources and validation cases, then you will see a bunch of really exciting, cool examples where we have been comparing Treble against measurements, against other simulation tools, and so on, and showcasing the added accuracy that Treble brings about. Okay, that was it for me. Thank you so much for listening. I look forward to the Q&A.
Okay, thank you to Ethan and Bradley and Finnur for these great presentations. We're a little bit short of time, but I think we're gonna add around 15 minutes to this webinar. I hope you will stick with us for some Q&A. I will just dive right in. This one is for you, Bradley. How do you present using Treble versus industry standard to clients? What is their reaction?
I'm not exactly sure what industry standard means. If they mean a simulation, a piece of simulation software that's been used up until now, some of the more popular pieces of software, CAT or EASE. I think. What's the question? What's the advantage of using it, or how I present the results, or
how do you present it, and what is their reaction? And they had industry standards in brackets.
Well, I think the fact that the Treble has the hybrid solver, for which you can increase the cutoff frequency, basically up until 2000 or even 4000 hertz. I forget what it was, depending on the room size. the hybrid solver is still very efficient. And you know what the benefits of using that solver, as opposed to industry standards, is that you have a wave-based simulation which models physical acoustic phenomena, which you would generally not be able to see using ray tracing software, which I think there is one or two programs which has some sort of very rudimentary diffraction model built in, or edge scattering. But since you are able to model that in a physical sense using the hybrid solver, you definitely have a huge advantage. And you using Treble, also you can show them how, if you put, for example, how a vertical surface receiver over a set of screens between working spaces, you can show how somebody who maybe has a voice with a lot of energy around 250 hertz or 300 hertz, you can show how that sound energy actually bends over the screens. So obviously people know that you can hear it, but you can show how much energy is actually getting over these screens. So I think that's generally a very impressive thing, impressive visualization for planners to see. They get a better sense of how sound physically behaves.
I would add to that too and say that standards, especially here in North America, for acoustics, focus on mid-band averages for reverberation time and perceived sound with barrier calculations or distance calculations, which are now included in the OpenOffice module, which is great. But we know actually from the research of how humans respond to sound is that there's more annoyance with low frequency contribution to sound. So having that available in the oralizations is super useful, because you could be meeting various standards, certain sustainability guidelines at the mid-band averages, but are you actually creating a space that feels comfortable? So watching the wave-based modeler improve over time is only going to bring us closer to really clearly conveying to clients what that low frequency control really means for the experience.
Absolutely.
Okay, great. Maybe one for you, Ethan. How was the podium for Oyas built? As a porous absorber or a membrane?
It's a work in progress. It's something that we've been experimenting with for quite some time, of varying the perforation sizes on the front of that panel versus its overall dimensions, but ultimately placing it in a back corner. We're actually modifying the podium that we have at the USM room in Soho right now, where the USM furniture actually has a metal perforated panel that you can slot into the front of the frame. So we're trying to calculate whether or not those are the right sizes, if we have to work with USM to create a custom panel with their team in Switzerland. So there's a few ways to go about doing it, but it's a combination of a membrane and diaphragmatic absorber in many ways. So it's stuffed with insulation. We have to create a custom material in Treble to do that. I'm curious to do some in situ measurements of it eventually with some sound intensity, and derive that to how we might be able to model that in the future. But yeah, that's sort of the more experimental side of the listening room sound design.
Thank you. Then one for you, Finnur. What is the lower frequency limit of the simulations? What is the lowest frequency to which the software is reliable and accurate?
That's a great question. We've set it around the lower limit of the 63 hertz band, so which I believe is around 50 hertz. In principle, we could go lower, and the wave-based solver in principle easily handles. You could go down to 1 hertz if you want, but we have some kind of post-processing mechanisms, filters, and so on that are introduced afterwards that limit this to down to 50 hertz. Some people have been asking to go really low, so that's kind of that's on our backlog, let's say, to go even lower.
Okay, thank you, Finnur. This one is for you, Bradley. We've encountered projects akin to your Atrium project, and usually we face constraints regarding budget and time that limit our ability to delve into room acoustics at the level of detail you described. Out of curiosity, could you provide insight into the hours allocated for the acoustical simulation, starting from 3D modeling to the analysis with Treble?
Yes. Okay. I think room acoustic modeling is, I think it's really an art, and the more you do it, the better you get at it. The more you know which details you can leave out, which scale you have to work at to include only objects and surface variations which are still acoustically visible for the solver. And I would say in the past, most time the most time was spent debugging the model. You know, you could, I mean, depending on the size of the model and how complex it is, you know, I've been able to get the model finished, you know, within one working day. And then this was more like when Treble first came out, and you didn't have the whole picture that was just presented. I would be spending a lot of time fixing the little holes in the model, and that actually is what took up most of the time. Was debugging the models. And for anyone who has experience with numerical simulations, like, you know, FEM simulations, you know that you know, getting the geometry in, getting it closed, getting good mesh was one of the most time-intensive tasks of the simulation procedure. And after that, you know, setting up materials, setting up sources and receivers, and I mean, that takes a matter of minutes if you have all the data available. And then you know, running the simulation, depending on the room size, has always taken anywhere between 2 minutes and I forget what the longest one was, but it wasn't very long. So actually, the better Treble has gotten over time, the more negligible the amount of time has become in setting up the simulations from start to finish. So I mean, I can't give an exact number of hours that it, because it, you know, varies on the model, but I think it's always been generally within the limit of what most clients like to or are willing to pay for a simulation.
Okay, that's great. Thank you. For you, Ethan, so really interesting cases. What parameter is most important when optimizing listening spaces, and how does organization help you in designing listening spaces?
I look at a few things. I look at the early to late energy ratios, in particular with small rooms. When looking above the transition frequency in particular, just making sure that there's an evenness across these rooms is super important. I'm not really designing many mastering suites in that respect, so I'm not only just looking at low frequency build up. It's really thinking about how sound scattering at the room boundaries plays a role at some of the mid to higher frequencies. And then with low frequencies, it is really understanding that modal response when using the surface receivers at the various planes, various walls, seeing if we're early enough in design, how affecting room geometry can impact the distribution of modes, and also furniture, like we mentioned with the podium resonator. And I would say those are the two most important things. So there's center time. It's also looking at clarity, but not getting too hung up on any one time domain of 50 milliseconds. There's some instances where we may want to look a little bit smaller than that. I do look at the impulse response plots quite a bit when I look at that time alignment with various speakers, which is really useful now that we have speaker import functions to see what, say, like a horn loaded system can actually perform and sound like in that time domain. So yeah, those are the parameters I really look at. Reverberation time is definitely important, but it's more to do with the energy ratios for sure.
Okay, and then there was, how does organization help you in designing listening spaces?
It's really, really, really important from a relative difference perspective of what an existing space versus where we can fully take this and then the in-between iterations look and sound like. But I've been really curious to find ways to capture the audio from those recordings and then pair them to the actual binaural recordings that I take and ambisonics recordings that I take from those rooms too. So it's a learning process. I think there's going to be a really interesting way to combine multiple order ambisonic recorded physical playback in those spaces versus the modeled playback, and understand what the differences are to then fine tune those for future projects.
Okay, great, thank you. So Finnur, we have a couple of questions about pricing. So could Mr. Treble throw a ballpark pricing for a small company, 1 to 2 acoustic consultants? And can you share pricing details for the software licenses? So
yeah, that's a very fair and understandable question. So we have an early bird offer we've had for quite some time now, which will last until the end of the year, which basically is $99 per month, unlimited users, unlimited usage. So that's valid until end of the year. And then we will introduce a public pricing, which will be kind of the pricing for Treble in the coming weeks, which will then sort of be valid from January 1st. And that is a model that is, we'll offer a couple of different options, either sort of a pay-as-you-go model, which is maybe more tailored towards kind of smaller businesses or maybe just using simulations every now and then. Then that's kind of lower price, but you pay per usage. Or another model, which we call more like the unlimited model, where you just pay a bit higher price monthly, and then you can use it as much as you want. And yeah, the exact numbers are coming very soon, and it's a seat-based model, so you pay per seat per user. So, but remember the early bird. That's the kind of just jump on that now, and then we'll work out the details later for the other stuff.
Okay,
that's coming.
Thank you, Finnur. We have a question for all of you. How confident are you choosing the absorption coefficients in the software, especially in the low frequency range? Does anyone have any experience with validation?
Well, there are not many. There are enough databases out there to, for example, the what's it called? Physikalische Technische Bundesanstalt, the PTB in Braunschweig in Germany, that once released a very large database of absorption coefficients, which were validated. And if I'm ever uncertain about something, I look into that database because I know that those components or materials have been tested in laboratories according to standards 354, and then the ones that I've worked with in Treble, I've always found mirrored in measurements elsewhere. So I'm personally very confident with the absorption coefficients, and I only use absorption coefficients that that I get from lab measurements from companies. And I don't make anything up.
Okay, what about you, Ethan?
Same thing. It's been interesting to see how some of these standards like ISO 354 have been evolving, and I know there's been some round robin studies that have been circulating across a few nations. So yeah, same here. Don't ever really select any materials that aren't measured in that capacity, but there are some experimental cases where we have some reference data for like that experimental resonator podium, where we have a rough sense of how that is contributing to the room with before and after measurements. So making sure that that's dialed in, and understanding, also comparing that with the literature to make sure that we're not overestimating or underestimating.
Okay, anything to add, Finnur?
No, I think these were really good answers, and it is sound absorption measurement at low frequencies. It's a tough problem, and there are uncertainties involved, and even with the standardized methods and so on. So users should be kind of aware of the limitations when they're inputting data. And I can also mention that we are introducing, or in the coming months, this material generator functionality, which allows people to set up their own kind of custom build-ups of materials, and use then sort of very well-established material models to estimate the absorption properties of those. That can be kind of another way to gauge how a material performs, and kind of, yeah, hopefully reduce a bit the uncertainty associated with this.
That's great. That's really great. I mean, because Treble already has the numerical solver within it, and you know, I think it's quite easy to model absorption coefficients numerically. So I think it's only a small jump for Treble to be able to just make simulations of different layered materials from different angles to get, you know, like a statistical absorption coefficient. So that's great news. Good
Yes, exactly. The kind of core, the engine of it is already ready. It's actually something we used to build some of the materials that are in the database, but the user interface part is being worked on right now.
Okay, we have time for maybe 2 quick questions. So this one is for Brad. Have you had situation where there was a large gap in results between wave-based and GA results? If yes, how do you deal with it?
Yeah, so for ray tracing simulations, the ray tracing algorithm begins to break down the smaller the room becomes, which is why it's so good to have the hybrid solver available, the wave-based solver available. So for the smaller the room, the more I raise the cutoff frequency of the wave-based solver, because then I know I'm getting accurate results. And if I but I have to be honest, Treble I've always seen a very good overlap between the geometric results and the wave-based results, especially for mid frequencies. Where it starts to really diverge is, you know, 250, 125, 63 hertz. And I mean, every model I've used so far has been able to handle a cutoff frequency at least up until 250 hertz, no problem. But for like very small, what do you call it, meeting rooms, I raise it up to 1,000 hertz, and then I have the wave-based results, and then the wave-based results converge with the geometric results. So there isn't really a problem there.
Okay,
maybe I can add briefly that, you know, this is also my experience, but also comment that you know, the acoustic parameters are kind of sort of not maybe a very detailed measure. So for example, if you're listening to oralizations or things like looking into the impulse response, then you might see some differences which are maybe not captured in the acoustic parameter. So sometimes we see some differences or can hear a little bit of difference as well, which is just as expected. These are 2 different modeling approaches.
Okay, I think we will have to stop now. I would just like to thank you all so much for joining the webinar and for speaking. And we look forward to the next one, and have a great rest of the day.